It's simply going back to another video. Today, guys, I'm gonna be going over the entirety of the AP Physics Simple Harmonic Motion Webassign. Without further ado, guys, let's get right into it. All right, you guys. So let's just start off here with problem number 1 up here. So, first things first. Read the problem. Which of the following statements are true? Select all that apply. The acceleration of particles proportional to displacement of absolutely directed. The motion is simple harmonic. That is true. In simple harmonic motion, the period is proportional to the square of the amplitude. That is not true. The period and the amplitude are not related at all. In simple harmonic, let me point this. And last one, in simple harmonic motion, the frequency does not depend on the amplitude. That is true. The frequency is entirely independent from the amplitude, since the frequency is dependent on the period / time and all that stuff. So, in this case, we're gonna have A and B equals true. So that's gonna be that for number 1. All right, now guys, on to question number 2. Sorry about that squeaky noise. If the amplitude, this camera's annoying. The amplitude of simple harmonic oscillators tripled. By what factor is energy changed? So energy is equal to, I believe, 1/2 a squared. I'm not sure. I know it's a squared somewhere. So if in this case we have, regardless of the 1/2, we have 3a squared. That's gonna be 9a squared. So it'll be 9 times 1/2 a squared, which is 9 times the energy. So it's gonna increase by a factor of 9. That is gonna be the answer. In my case, it's gonna be part D of the problem. Now, question number 3. All right, so question number 3. An object attached to a string has simple harmonic motion with amplitude 2.45 centimeters. When the object is 2 centimeters from the equilibrium position, what fraction of its total energy is potential energy? So, squared, but regardless of that, it's just gonna increase by a factor of 9, no matter what the other values are, because you're gonna multiply by that. So, in this case, equals 1/2 ka squared. So here we have this is going to equal to something. So 1/2 k times a squared. A is going to be 2.45 squared. 2.45 squared. Let's get a calculator out here. All right, so 2.45 squared, 6.0025. 6.0025 times that, blah, blah. Here we have 1/2 k squared. This is just law of conservation of energy, guys. This is going to be total energy. It's going to be energy at a certain point. So 1/2 k squared, 1/2 k x is going to be 2. So 4 squared. 2 divided by 3 is going to be 2/3, because this is, since the k's are the same, plus 1/2 mv squared. So now, if I explain this right, 2k right here, this is about 3k. Is 1/2 mv squared. So in this case, these energies added together will be 3k total. So since this is 2/3 of that, that means that the how do you say it? The potential energy is gonna be 2/3 of the whole thing. If that makes sense. Just because that's 2/3 of that. That's because one of them is 2/3 of the total. So, all right, now guys, on to problem number 4. Pendulum A has a bob of mass MA and a length LA. Pendulum B has a bob of mass MB and a length of LB. If the period of A is twice that of B, which of the following statements are true? All right, guys, now on to problem number 4. So we have a pendulum has a bob of mass MA and length LA. Pendulum B has a bob of mass MB and length LB. The period of A is twice that of B. Which of the following statements is true? So we know that we have period of bob A It's going to be 2 pi square root of L over, well, L of A over G, which is 2 times 2t, well, I suppose, yeah, this would be 1/2 t, but it's 2 times t of b, t of b would be 1/2 t of a, which is just, in this case, pi square root of lb over g. Now if period of a is going to be 2 times this will be, for period of a, we'd have 2 times pi times 2 square root of lb. You can rewrite this however you'd like, but that's going to be period of a essentially, right there, in terms of lb. And now to find this in terms of, to find the like proportion of lb, I guess, like you just and since mass is not included, we know that's going to be one of the answers where it's regardless of like whatever the ratio of the two, so you can already eliminate something with that. But now to find which one it is, put that in square root, you just let's find the square of that and square root that square, so it's going to become right here 2 pi square root of 4lb over g. To find the that is going to be our answer right there. 4 LA equals 4lb up here, just like that. Alright guys, now on to problem number 5. Position of a particle is given by x equals 5 centimeters cosine 7 pi t. Okay, so x equals 5 centimeters is the amplitude, cosine of 7 pi times time. Okay, cool. T is in seconds. Alright, so part A wants us to find the frequency. Frequency is going to be frequency is angular frequency. Since angular frequency is 2 pi times the frequency, frequency equals angular frequency over 2 pi. Angular frequency in this case is going to be the 7 pi part, so we know that this is going to be 7 pi over 2 pi, which equals 3.5 hertz, guys. That's going to be our frequency over here. Now part B, we have, what is the period? Period is going to be 1 over frequency, which is going to be, you could always just type in 1 divided by frequency. 1 divided by like 1 / this number into Webassign, but the actual value is going to be 1 divided by 3.5. It's going to be well, so I'll just write it out actually. T equals 1 over f equals 0.286, rounding to significant figures in seconds, just like that. Now for part C over here, what is the amplitude of the particle's motion? We know the amplitude is going to be this part because this equation is just in the form x equals a cosine of wt plus phase change over here. Phase change in this case is going to be 0. This is going to be the a equals 5, so amplitude is 5 centimeters. Just like that. Part D, what is the first time after t equals 0 the particle is at equilibrium position? So, well, there's just moving at the time. So, all right. So we know the cosine starts up here. So it's gonna move. So let's just draw a graph here. We have this right here. Cosine go like this, like that. So we know that we're trying to find this point here. It's gonna be the time, and we know it's gonna be moving in the negative direction. Because of the way this graph is formed, is shaped. So we can already answer the last part, but now as for the actual time, we can just, I'm pretty sure, just do position equals 0 equals 5 cosine, because position is going to be at 0, cosine of 7 pi t, solving for t, so we just do 0 cosine of our cosine of 0 is going to be 0 or pi, 0 times 0, 0 times pi. Times pi. Is time pi? I don't know. 7 pi divided by pi. 2 pi. Wait, no. It's going to be pi over 2. Sorry, my bad. Alright, so this will become arc cosine of 0 equals 7 pi t. Arc cosine of 0 is going to be pi over 2. And then divided by 7 pi over 7 pi equals the time. So now this is going to be the equivalent of 1 over 14 just because of that. And that is going to be your answer, guys. You can type it in as 1/14 in this case, or you can always just calculate that. Alright, so on to problem number 6, guys. I apologize for all that blurred out answers. Right now, it's just because most of this website I've done so far. Once we get to a point where I haven't done them yet, we will be able to do them together, and then we can actually put in the answers together. But until then, guys, we're just gonna work with what we have. So, all right, problem number 6. The period of an oscillating particle is 16 seconds, and its amplitude is 17 centimeters. Oh. At t equals 0, it is at equilibrium position. The distances traveled during those times intervals. So, we know that period. So we know that period is 16 seconds. We know that this is going to be the graph. It's at equilibrium position here at time equals 0. Amplitude 17. So up here, this is going to be 17, negative 17, right here. Oh god, I'm sorry guys, I'm off the thing. So now, 17, negative 17. We know that this period to get to here, time equals 16 seconds. So now, in order to find 0 to 4, 0 to 4 is just going to be a quarter of this. So we know it's going to be at the amplitude, so A is going to be 17 centimeters, just because that's going to be a quarter of the way there, and a quarter of the way is at the amplitude, just because of properties of sinusoidal functions and knowing the period. Now, 4 to 8, same thing, guys. It's just going to travel 17 centimeters, just because that's the distance, hear me out. It's just gonna come back down basically from what I just did. Next up, 0 to 2. 0 2 0 2 0 2. What I do to solve this, I forget. Alright, we know, so let me figure this out. T. How did I do this? I forget. Alright, anyways, so let's see if I can figure this out. So, alright, so we have this equation now with sine. So we know that position x equals amplitude times sine of angular frequency times t with no phase change there. At time, so from 0 to 2, we know that it's going to be just the time, time 2, so x equals 17 sine of w in this case. W equals 2 pi over t, just because we don't know the angular frequency otherwise. 2 pi over t, 2 pi over period. 2 pi over 16 is pi over 8. Pi over 8 times, what is it, times 2 seconds is going to be x equals 17 sine of that, sine 2 over 8, sine pi over 4. Sine pi over 4, what's sine pi over 4? Sine pi over 4, root 2 over 2. Root 2 over 2, 17, 17, root 2 over 2. 17 root 2 over 2. 17 root 2 divided by 2. Yeah, and that's going to be, guys, 12.0 rounded there, yeah. That makes sense. Let's do this out to find x. That's going to be the position. That is the answer to part C. 12.0 centimeters. And now, guys, from to find from 2 to 4, it's always just the remainder of the way. Here, I'll expand this real quick. So this will be the beginning. Goes like this, up to 4, 2, up to here, 12, and now we know that this is 17. So it's just gonna be the difference between these two. So difference between these two. So 17 minus this, which in this case I just put in 5, but it's 4.98 if you guys want to be precise. 4.98 centimeters. And that, guys, is how you're gonna find the answer to question number 6. Sorry, my chair's so long. 7. So in this case, 7. An object of unknown mass is hung from one end of an unstretched spring and is released from rest. That means that it's going to be starting here. The motion is going to go like this. It's going to be sine waves starting from rest at the equilibrium point. Release goes down to up to 3.39, down to negative 3.39, I believe. If we're coming to rest, find the period of the motion, blah, blah, blah. Period. So in this case, since we're not giving anything else, I think that it's going to have to be probably like, we're going to have to generate 2 equations, obviously, and 2 unknowns in order to find one thing to cancel them out. So we have a potential energy mgh at bottom point. Here's our thing. It goes down this distance, 3.39. We have mgh here. mgh. H is going to be this baseline point right here. And then this point right here is going to be 1/2 kx squared, law of conservation of energy. H is going to be, x in this point, I suppose, right? Yeah. And then, so this is the exponent. We're left with k equals 2mg over x. K equals 2mg over x. Now, what other equation has k? The angular frequency, which is also going to help us find the period. Angular frequency equals square root of, I believe, mass over k, or k over mass. Therefore, w squared times m equals k. So these equal to each other. We know that w squared times m equals 2mg over x. Cancel out the m's. W squared equals 2g over x. W squared, w is also equal to 2 pi over t, since t equals 2 pi over w, so it's like switchy. This squared, find the period. The squared, square root of that, so in order to finish this, plug this into here, that squared, then we're just going to do 2 pi over square root of 2g over x equals t. Just do a little bit of algebra there. Once you plug that in, plug in our values, is going to be 2 pi over square root of 2 times 9.8, which is g, over x. Our x value is 3.39 centimeters, or in this case, actually, sorry, it's going to be meters, so 0.039 meters. Oh, sorry, actually, I messed up. It was 0.339 meters, which equals 2 times 9.8 divided by 0.0339, square root of that, 2 times pi divided by that. It's going to be 0.261 seconds. That is going to be our period right there, guys. Sorry about the mix-up. Yeah, I sometimes leave stuff out just because I tend to try to go fast and I mess up somewhere. So yeah. All right. Anyways, let's keep going. Number 8 down here. Let's go down to it. The phase of a certain simple harmonics oscillator is 0 when t equals 0. Well, if the oscillator's frequency, what was the phase? The phase is gonna be, so we know that the phase is equal to Wt plus phase constant, which is actually the part in the in like all the cosine functions that you see in the popular equation, x equals a cosine of Wt plus phase constant. I personally don't like these so much, but let's give this a shot. So I forget how to do this one, but let's try it. Phase is phase is blah blah. When is its phase blank? We have to solve for t. So first, at t equals 0, we know that phase is 0, therefore phase, oh god, phase equals w times 0 plus this will be 0, so phase equals phase constant, which means that the phase constant is 0 since that is 0. So phase constant is 0 in this case, so we don't need to worry about that in our calculations. So now literally what tells us is that these calculations entail only W and T, which we are basically given here. So for part A, we know that the phase is going to equal to Wt plus phase constant, which is a 0, so Wt, W is 2 pi F times time, and now we are given that it's going to be, phase is going to be pi over 6 equals 2 pi times 5.15, that's going to be our frequency, times time. We're solving for time, so pi over 6 divided by all this, 2 pi times 5.15 equals t, which our t is then going to equal, so let me try this, pi divided by 6 divided by 2 divided by 5 divided by 5.15. It's going to equal 0.0162, yeah, 0.0162 seconds. And that, guys, going to be the answer to part A. Now on to part B. So we'll just make that up there. Part B. So part B. What instance does it next have the same position and velocity as in A? So, alright. So we got this out. We have this. Blah. Let's say this is time. Blah blah. Same velocity here. Oh, after one full cycle, so it's gonna be. Oh, we know frequency. Okay, so it's gonna be 1 divided by the frequency, so 1.51. That's gonna be that plus this value here, right? Plus the value we got in the first part. Okay, so it's gonna be 1 divided by 5.15 plus the answer. Yes, it's gonna be 0.210 seconds. And that, guys, is going to be the answer to part B of number 8. Alright, guys, now on to problem number 9. So first of all, what we're going to do is we have distance, we have amplitude, cosine of this Wt, and the phase and phase shift. Phase shift is going to be this. Phase shift in this case, since this cosine is going to be negative pi over 2, sorry. So here in this case we have 5, so we have negative 0.05 meters equals 0.15 cosine of WT. WT is 2 pi f of t, and t is going to be a 0.76 because angular velocity plus minus pi over 2. That's just like the fate that you have to get from what do you call it? A cosine to a sine. Well, that's what opposite sine, but yeah. Alright. Now, how do you do this? Now we just solve for f basically, so divide both sides, negative 1/3 arc cosine of this equals all of that. So divide by, well, first of all, plus pi over 2, all divided by 2 pi times 0.76 equals f. My f's are weird right now, sorry guys. So then to do that, we just do calculator, arc cosine. Actually, make sure we're in radian mode, yeah. So arc cosine of 1 divided by 3. Well, arc cosine of negative 1 divided by 3. It's that plus pi over 2. Do that divided by 2 divided by pi divided by 0.76 is going to be f is going to be 0.729 hertz or seconds to the negative 1. And that, guys, is the answer to number 9 right there. She's given an initial downward velocity of 1.8 meters per second. How far below her equilibrium position does she go? Alright guys, so this is the sine function of the maximum velocity. In this case, it's going to be at the equilibrium point, obviously. So here we have our sine function. We know Vmax is equal to W times amplitude. We're trying to find, in this case, how far below the equilibrium point does she go. That's literally just the amplitude, because that's the distance from the equilibrium. That's basically definition of amplitude if I haven't seen it. Velocity mass is going to be 1.8 divided by W, which W in this case is going to be square root of, I believe, K over M. Yes, K over M equals A equals 1.8 over square root of 420 over 46, which equals 1.8 divided by square root of 420 divided by 46. Which equals 0.596 meters. That is going to be equilibrium. That is answer to part 10A. Now part 10B. Part 10B. Where is she when she has an upward velocity of 1.2 meters per second? So here, to find this point, we'd have to find the position at a sine of WT. We know that the velocity is WA cosine of WT. In this case, the velocity would be negative 1.2 equals WA. W we solve for up there, square root of 420 over 46 times A is that 0.596 times cosine of square root 420 over 46 times T. We're going to solve for T. We'll just do that out. We do it on my calculator. So we have square root of 420 divided by 46. Annoying one, but yeah. Negative 1.2 divided by that divided by 0.596. Arc cosine of that divided by the root, t equals 0.77, t equals 0.7611946591. Now we have the time at that certain point. We can plug our time back into this equation right here to get that the x equals our amplitude 0.596 times sine of 420 square root of 420 over 46 times a value for t 0.76119 blah blah. In order to get that, our position is going to be this times this sine of that times value point blah blah. It's going to be x equals 0.444 meters. And that is the answer to part B. Now on to part C. And also, guys, it's going to be 0.444 meters, just because plus or minus, sorry guys, because look at if you look at the graph, there will be multiple points at which it has velocity of upward velocity 1.2. It could be like, say, here and here. I don't actually know what like it is, but I don't know if it's like here and here, but like there will be multiple points on either side, so that's why it's plus or minus, because there will be points on the positive and the negative where it's upward velocity of 1.2. Yes. All right. Now on to part number C. What is her acceleration? Describe the position in A. Position in A. It's gonna be it's gonna be the amplitude. So acceleration equals w squared of x. So in this case, we can just plug in our x, w squared. It's gonna be 420 over 46 times 0.596 equals, well, technically would be negative this, but because it's the equilibrium, because it's the thing, I guess it's not. I don't actually know why it's not negative, but it is what it is. Oh wait, no, yeah, it's because it's at that set point. It is gonna be positive. That makes sense. Cross that out because the x would be negative, so times negative that. So, all right, so 420 divided by 46 times magic number 0.5956 blah blah. It's gonna equal 5.44 meters per second squared, positive, because it's gonna be negative x right there at the beginning. And now D, what is her acceleration? The position described in B. It's gonna be plus or minus something, plus or minus acceleration, plus or minus same thing again, equals plus or minus w squared. X is gonna be 0.444, which is gonna be, so 46 420 divided by 46 times 444 number 4.064 meters. That is the answer to part D. Yeah, right there. All right, now number 11, a big one but easy one and very merry one because it gives you a lot of points very easily. If you're looking for points, I recommend doing this one probably first. So let's get started. A particle executes linear SMH, it's a SHM with frequency 0.22 hertz. Oh my god, can you stop squeaking? So F equals 0.22 hertz. We know point x equals 0, t equals 0 has the displacement, blah, 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 and 0 velocity. For the motion, to determine the following. Displacement, that's just the amplitude in that case. Determine the following. The period. So start off with A, t equals 1 over f, which equals 1 over 0.22, which I just wrote down as 1 over 0.22, which you can do as well, or just 1 divided by 0.22. Wait, nope. 1 divided by 0.22, which is going to be 4.54, 4.55 seconds. You can do that as well. Now, angular frequency, can't speak, dude. Angular frequency, in this case, is going to be W is 2 pi f, which you just multiply, so it's 2 pi times 0.22 hertz, which equals 2 times pi times 0.22, 1.38 hertz, right, or radians per second. 0.38 radian per second, my bad. Alright, now C, amplitude is going to be 0.45. We already established that. The displacement is that much earlier on the problem. Just the description, just reading the problem essentially. Part D, displacement time t. So that's just going to be our equation for displacement. X equals a cosine of wt plus phase shift, which in this case, phase concept in this case doesn't exist. That w in this case is going to be 1.38. So here we're going to put in x equals 0.45 cosine of w 1.38 t. So these are going to be the things that they're asking us to put in. We're going to put that in as well. Velocity. Oh gosh, I hate this. Actually, it's quite annoying. Oh, actually, no, it's not annoying. Hear me out. The velocity equals w a sine w a sine of wt, because it's the. Sorry, I got stuck up there because I thought of something different. Because the derivative of this function, negative that. So velocity equals negative WA, negative 1.3 times 0.45, which is going to be negative 0.621 sine of W again, 1.38 t. These are going to be the answers we're going to have to put in. Negative this, positive that. Alright, now for part F. Alright, is a function, dude. It's so funny. Part F, maximum speed, velocity max equals WA, which WA has already been established to be that. That's what just positive version is going to be 0.621 meters per second. F, now into part G. G, maximum acceleration max. W squared A? Yeah. That's going to be maximum acceleration. What am I saying? Alright. W squared A equals W squared 1.38 squared times 0.45. It's going to be 0.857 meters, centimeters per second squared. It's going to be centimeters as well, by the way. Centimeters second squared, not meters second squared. Sorry, guys, I keep turning it back towards me. I hope that you guys can still read it just fine. I hope that it's not too much of a mess. Oh, gosh. I'm looking at it right now. It's a bit of a mess. I'm sorry. Alright, G. Let's move on to part H. Find the displacement at t equals 3 seconds. So, equation again. X equals a cosine of wt, we know A, we know W, we know T in the situation, so just plug it in. X equals A point 4.5. We just literally use our equation from above. Cosine of 1.38 times 3, which X equals 0.38 times 3. Cosine that times 0.45. It's going to be negative 0.244. Negative 0.244 centimeters. In this case, H. Last part I. Let's do the speed at t equals 3. So just again plug into our equation. V equals negative 0.621 sine of 1.38 times 3. So sine of this times negative value above is 0.522. Velocity equals 0.522 centimeters per second. Just like that, guys. That is 11 finished up, quick and easy. Yeah, that's that. Block is on a piston that is moving vertically with simple harmonic motion. Simple harmonic motion. If simple harmonic motion has a period 4.2, what is the amplitude of the motion with the block and piston separate? That means that essentially, so separated pistons are here. Block is up here. The block goes this way. What velocity? What position? What amplitude? Sorry, if it goes that fast, what rate? That means that the acceleration equals 9.8 meters per second squared upwards. For it to just separate, that would be the threshold, essentially. That's what it's saying. If period of that. So we have to find. So we know that A is the angular frequency squared times displacement. In this case, displacement would have to be the amplitude. To find the amplitude, we'll negative that. Amplitude, there you go. Amplitude, in this case, we're given the period. T equals 4.2. We know that W equals 2 pi over T, which then equals 2 pi over 4.2. 2 pi by 4.2 is that 1.49. 5996502. Put that into our equation. Squared that 9.8 meters per second squared equals that. So divide by this 9.8 divided by that equals 4.3 here. In this case, it won't be negative. It will be absolute value equals. So I'll just type it out. 1.495 squared A equals 9.8 over 1.495 squared equals 4.38 meters. And that, guys, the answer to part A on number 12. So that's part A. Now for part B right here. Part B, if the piston has an amplitude of 1.5 centimeters, what is the maximum frequency for which the block and piston will be contact continuously? Again, this will be a threshold, so at 9.8 meters per second squared, it will be the case. They will still be together, yet just apart. It's a weird concept, but it's weird conceptually, but like mathematically, it makes sense for that to be like the case for both. Like it's the point where it like just stays on, like the maximum point stays on, but it's also the point where like it'll just separate if it's just above. It's weird. What is the maximum frequency for the block and piston will be contact continuously? So we know that again, acceleration have to be 9.8 at W squared. times amplitude 1.5 centimeters, or in this case 0.0. I don't know if it wants us to, but yeah, I'll just do it in meters. 0.015 meters, probably don't want us to just because of the acceleration. So now per second squared. We know W equals 2 pi f, because it's talking about frequency, so we're going to use that. Maximum frequency is going to be at this point where the acceleration is 9.8, so 9.8 over 0.015 square rooted is going to be W. W is this, so that's going to be 2 pi f. 2 pi f. Divide all this by 2 pi equals f. F equals this. Square root of 9.8 divided by, so square root of 9.8 divided by 0.015 divided by 2 divided by pi. It's going to be that. It's going to be frequency. It's going to be 4.07 hertz. Right there, guys. And that, guys, is the answer to part B of question number 12. Alright, guys, on to problem number 13. As you can probably see, I already did some work from this and erased it because I tried it and I was wrong the first time, because I went into I dug myself a really deep hole that I couldn't get out of, and I was like, oh wait, I know what I'm not getting out of this, I don't know how to do this yet. So I'm gonna do it again in the way that I know how to do it, that's gonna work, even though I thought my way would be faster, which it turned out not to be. So we know the mass equals 1.4 kilograms. We know that K value is 140 Newton per meter. So if we're asked for a W value, it's going to be square root of K over 1.4, which is square root of K is 140 or 1.4, which is going to be 10 because it's square root of 100. 10. That's the angular frequency, radian per second. I'll do that now, guys, because we'll need it later. Now, so part A, as for the amplitude, so when t equals 0, the positions of velocity, blah blah, are these. So as for the amplitude, so in this case, we're going to have equation for position, amplitude cosine of angular velocity t, plus phase constant, which we don't know yet. Velocity equals negative AW, whatever you want to write it, sine WT plus phase constant. Now we just plug in our values for t, which is going to be t equals 2 seconds. Velocities that were given, velocity and displacement that were given. Velocity displacement 0.129 equals a cosine of 20 plus phase constant, and then 3.415 equals negative 10 a sine of 20 plus phase constant. Now in this case, we can just solve for, well, put a on both sides and solve for the phase constant, and should be chilling, right? I believe so. Alright, so let's do this. To get a on the side, divide by a. Oh, divide by this. So okay. So 0.129 over cosine 20 plus phase constant equals a, same thing on this side, which a also equals 3.415 over negative 10 sine 20 plus phase constant. Alright, now set these equations equal to one another to find the phase constant. We'll put the phase constant back in order to do that. Multiply both sides. cross multiply. Alright, so we'll have negative 1.29 here, sine 20 plus that. And then we'll have goes 3.415 cosine of 20 plus phase change that. Guys, again, I'm doing this problems for the first time, so if I am quite slow on these, I'm sorry. I'm kind of trying to learn these with you essentially. Here you probably divide this side by that, this side by that, so this becomes sine 20 plus this over cosine of 20 plus phase changed equals 3.415 over negative 1.29. This is going to become tangent of this. Tangent opposite of this is going to be 20 plus phase change. So arctan of 3.415 over negative 1.29 equals 20 plus phase constant. That minus 20. 3.415 divided by negative 1.29. Arctan of that. Subtract 20. Negative 21. That's the phase constant. It's going to be negative 21. In this case, put that back into our equation to solve for A. We'll do displacement equation. So equation 0.129 equals A cosine of 20 minus 21.2. So 20 minus 2 cosine of that. It's that 0.129 divided by this. So A is equal to 0.365 meters. Alright. 0.35 meters. Is that correct? That is correct right there, guys. Alright. Now, moving on to part B of that. B, mass velocity at t equals this. Alright, so now we have the amplitude, we have everything, so basically all we can do now is just plug in an equation. So x equals amplitude 0.365 cosine of wt, t is 0, so this is 0, cosine of negative phase constant, which is, well, cosine of our phase constant, which is going to be negative 21.2, and then velocity is going to be negative 10 times this, which is going to be negative 3.65 sine of wt is 0, minus 21.2. Now just do those out. So we have cosine of phase constant times 0.365 negative 0.259. That'll be the answer to part B, and then part C, velocity is going to be equal to that equation. Sine of, sine of this value times negative. Where's our thing? Wait a minute. Hold on one sec. This times this. Alright, chill. And now we can do, sine of this, sorry, times 3.65. In that order, 2.57. And that, guys, should be answered to both of those. Just double check. Negative 0.29, 2.7. There you go, guys. That's the answer to question 13 right there. Right now. On to problem number 14. So 14, we have this graph right here. It's the acceleration. So we know that the acceleration is the second derivative of the position. We know that it is the first derivative of the velocity. So now, corresponds to it being a negative xm. That means that's on an x. This is going to be negative xm, and it's going to be positive xm. That's just the amplitude. It's just the maximum points, just like this. Blah, blah, blah. So now we have our say we had a cosine function as the x. That means that the first derivative is going to be negative sine, and the second derivative is going to be negative cosine. So in this case, essentially, what this is telling us is that if this was a negative cosine function, our initial position cosine function would go like somewhere like this. So we have to essentially see the points to opposites, which is why corresponding to a particle being at negative max is going to be one of these dips right here, but it's going to be the opposite one of the things. So in this case, negative max is going to be point number up here 2, because that's where the farthest dip would be. If sorry, this gets off like right here. None of this really exists in this graph. Ignore all of this. There's this one right here. That'll be a negative right here. So that's why the first one is number 2. That is more of a conceptual question than anything else. All right, now ask for for part B. 2. Part B, at point 4 is the velocity of the particle positive, negative, or 0. Point 4 is when the acceleration is 0. So say we had, this is a negative cosine graph. That means that a negative sine graph would be like this. So as you can tell, that would mean that like at this time it would be, I think around the apex, right? Or a little bit. Sorry, because this is already dipping right here. It'll be like a little bit. How will this be shaped again? It'd be like this, basically. Something like that. Like it would be there. So whatever, like no matter what, it would be positive anyways. That's just because the velocity, that one. So positive, and now C. C at 0.5 is the particle at negative maximum, at max plus maximum. As like I said, guys, the maximums would have to be one of the peaks, so it can't be either of those. So that eliminates for my situation, A and D. At 0, no, it's not at 0. Like I said, it has to be at the peak, so it has to be between one of the numbers, one of the between options. So that already eliminates quite a lot. And then between negative m and 0. So as I said, guys, it would flip it around. So at 0.5, it would have to be between 0 and positive x maximum, because like I said, guys, it flips around because of the derivative situation that we have between acceleration, velocity, and position, like I said, guys, this is position equals a cosine wt. Velocity equals derivative of that, which is negative wa sine wt. And then the acceleration is the derivative of that, which is going to be like in respect to t is, guys, d dt. Derivative of respect to t of these functions is going to be so you guys can see that dt squared negative w squared cosine wt. And guys, this is equal to right here negative w squared cosine wt, because as you can see, guys, amplitude, and we know that amplitude cosine wt is equal to x, so in this case is equal to negative w squared x. Now, guys, is why the equation a equals negative w squared x works, is because it's just the second derivative of this function right here, and this value is x, basically. That's all. Alright, guys, now on to problem number 15, because that was a little quick and easy lesson right there. So, number 15. A large block P executes horizontal simple harmonic motion as it slides across a frictionless surface with a frequency f equals 1.2 hertz. Okay, so f equals 1.2 hertz. Block B rests on it. Oh, not these questions. Bang, bang. Block B. Alright, so the coefficient stratification friction between the two is, so mu sub s equals 0.55. Alright, awesome. What is the maximum amplitude of oscillations that the system can have if block B is not the slip? Alright, so mu sub s, well, on that one, I assume it's the frictionless. Yeah, okay, first surface is frictionless. Alright, so we have to find the normal force of this one on there. Force of static friction equals mu sub k Fn, which equals mu sub k mb times gravity, and then F equals mass times acceleration equals u sub k mb gravity, mass times acceleration, this will be the mass, blah blah, gravity A equals mu sub k gravity, mu sub s, sorry, I'm so used to mu sub k problem, sorry, mu sub s gravity. Does that make sense? That doesn't make any sense. Now, whatever. The acceleration, the maximum acceleration such that they can have is well, let's do that out. Equals 0.55 times 9.8 meters per second squared. 0.55 times 9.8, 5.39. That is the maximum acceleration they can have. So now we have A max equals negative W squared A, I believe. We know the frequency, so therefore we know W. 5.39 equals negative W, so W, so we know F equals 1.2, W equals 2 pi F, therefore W equals 2 pi times 1.2 to 2.4 pi equals 2.4 pi squared, so this divided by 2.4 pi squared equals amplitude. This will be the absolute value. Squared, parentheses squared, 5.39. Oh yeah, 2.4 pi squared. How about that? Ooh, that does not sound right. Oh yeah, in centimeters. Equals 0.0948 meters equals 9.48 centimeters. Let's try that out. What? 48. And there you go, guys. The answer, let's try that better. Equals 9.48 centimeters. Alright, so essentially, guys, what this one is, sorry I kind of rushed that a little bit. I kind of wanted to figure it out, like, make sure I get it first, but it's going to be even harder to teach because I kind of just ran through it like I was doing it instead of actually explaining it. So that's probably the issue with me doing this while I'm teaching it. But yeah, alright, so we have the blocks moving like this. Basically, what's keeping them together is the force of static friction here. While the force of static friction is keeping them together, it can't exceed a certain acceleration. Otherwise, the force of static friction will, they will essentially they will pull apart if it exceeds a certain acceleration. And to find the acceleration, the threshold, we have to find the force of static friction, which is going to be mu sub s over m, times mb. G, because it's the mass pulling down. The other mass is on the frictionless. And like, yeah, the friction between the two doesn't. This object's mass does not impact the friction between the two. Essentially, what I'm trying to say. Because top object that does that, and now, Newton's law, force equals mass times acceleration. Find the maximum acceleration, because maximum acceleration is from that force like that. Because conservation of force. Wait, force conserved. I don't. Hear me out. All right. Use Newton's law to show force ma. You can cancel out the masses to get just the acceleration in terms of mu sub k and g, which is the known values. Mu sub s and g. Mu sub s. Let me just rewrite those because I don't like this. Mu sub s and g. So acceleration mu sub sg, which is this value right here, 0.55 times 9.8, which equals this right here. That is going to be the maximum acceleration it can have. So in an oscillation, maximum acceleration, blah blah blah. Maximum acceleration is going to be at the amplitude. So it's going to be w squared times amplitude. W squared, wa is angular frequency. We are given the frequency. The angular frequency is 2 pi times frequency, which is 2.4 pi in this case. So 2.4 pi squared times the amplitude will give us the maximum acceleration. Therefore, the maximum acceleration divided by 2.4 pi squared is going to be the amplitude, and therefore we solve for the amplitude in meters times 100 to get centimeters right here, because it asks for centimeters in the question. Voila. That is question 15 in a nutshell. Alright guys, now on to problem number 16. Ignore the little red things there. I gave something a try. It didn't work, but I think I got the right method this time. And oh my god, get in this chair, stop, please. Alright, and now we're just gonna do it. We're gonna see what works. I'm pretty sure it'll work this time. Let's just give it a shot. So particle mass 3 kilograms attached to a spring of force 300 newtons. So we have 3 kilograms mass, 300 Newton meters, oscillating on a horizontal frictionless surface. So we have 3 kg going back and forth, horizontal frictionless surface, 300 Newton meter. Oh, I'm going scribbles. Amplitude is 2, so 2 meters, 2 meters. All right. A 7 kilogram object is dropped vertically on top of the 3 kilogram object as it passes through its equilibrium point. Alright, so equilibrium point is dropped on. Two objects stood together. So at equilibrium point, it's going to have its maximum velocity. For the first object, the maximum velocity is going to be the angular frequency times the amplitude. Amplitude, we know, is 2. Angular frequency is going to be square root of k over m square root of 300 over 3, which is going to be square root is 10. 10 times 2 times 2 is 20 meters per second. That's pretty fast. That's before it was dropped on. Now let's use law of conservation of momentum to find the velocity after. So initial velocity m1 v1 plus m2 v1 initial, I guess, v1 v2 initial equals m1 plus m2 times the new maximum velocity that's new at equilibrium point again. So let's do that. So this will be 0 because the second object's coming straight downwards onto the block. It's coming straight downwards onto the block right here, meaning that it will not have any horizontal velocity. Therefore, we can it's negligible. So this would become 3 times 20 equals 10 V max here. New V max. Oh my god, I can't even spell. New V max divided by 10. That's going to be 60 divided by 10, 6 equals velocity max of both. Now we can use law of conservation of what's it called? Energy to find the amplitude of the new one. So 1/2 of a combined mass is going to be 10 times new velocity times maximum velocity, 6 squared equals 1/2 k a squared. We know kk is 300. We can just put in 300 here. 300. Cancel out the 1/2. We just do this out. 6 squared, 36 times 10, 360. 360 divided by 300. 360 divided by 300 square rooted. Give us a is equal to 1.095. So 1.10. 5115. That is a new amplitude. So to find the difference in amplitude, we take the old one, which is 2. 2 minus this. 2 minus that is 0.905. 0.905, and that, guys, should be the answer for the change in amplitude. Let me just make sure. 905. Alright, that's correct up there. Now, okay, how does the period change? Clearly, it's not no change, guys. I apologize about that mistake up there. I made a rookie. I mean, not a rookie. I made a careless mistake when I calculated this the first time, which gave me the wrong value. And then, oh wait, actually no. For the other ones, I put them in, but I didn't tip submit. And when I submitted my attempt for the first part, it just didn't go. So I'm sorry about that. How does the period change? So period equals 2 pi of m over k. So if initially, so m initial equal, so m1 we'll say equals 1 to 2 equals 2 pi square root of m1 plus m2 over k. That's going to be a new period because it's going to be combined masses over k, blah, 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 equals this instead of this, the first mass. So first mass over k, 3 over 300, 1/100th. 3 divided 300, square root of that, times 2 times pi is that. So 0.628. Second period is going to be 10 divided by 300 divided by 300 square root of that times 2 times pi 1.14. So this becomes 1.15 seconds. So the period increases. Period increases by how much? Minus this. The period increases by 0.52519 seconds. Yeah, let's go back to that. You just take the magnitude of the difference of those two. Just 0.591. So it increases by, which is actually kind of counterintuitive, 0.519. Actually, it's not because you add weight, so it makes sense that it's like slower, I guess. All right, so those two are correct. Now, for the last one, in terms of energy, how much does the mechanical energy of the system change? I believe that it should decrease because the velocity decreases. Makes sense. Yeah. So we'll start off with for C. Let me see here. All right, so it should be 1/2 m1v squared, and then 1/2 m1 plus m2 v squared, v1 v2 squared, v2 max, v1 max. All right, so v1 max was that the initial velocity was 20 squared 400 times 3 divided by 2, 600. Then we have 1/2 those two combined squared, 6 squared times 10 divided by 2, 180. So it makes sense. It decreases 600 minus 180, 420. Decreases by 420 joules. And voila, guys, that is the answer to problem number 16, A through C. Obviously 16D, it says account for the change in energy. I'm gonna let you guys do that on your own because it's an open response one, so but you guys can do that. So, alright guys, now on to problem number 17. So 17 part A. 17 asks, in an engine a piston oscillates with simple harmonic motion so that its position varies according to the following expression, where x in centimeters and t in seconds. X equals 6 centimeters cosine of t plus pi over 7. So question letter A asks, at t equals 0, find the position of the piston. So in this case, we just plug in t equals 0, so x position equals 6 cosine of 0 plus pi over 7, which is just pi over 7 in this case right here, right? So now just calculate that. Calculator, cosine of pi divided by 7 times 6 is 5.41. Part B, let me just make sure that's right. 5.41 centimeters. Part B is going to be using the velocity equation, which is going to be a derivative of that, which is going to be W seems to be 1 in this case, W1, so negative W1 negative A sine of t plus t is 0 in this case, 0 plus pi over 7. Just like that, pi over 7. In this, you just plug in stuff into the equation and the derivative of that equation, and you'll be fine, guys. It's actually like I'm happy with this one. This is probably the easiest problem yet. Well, at least one of them. Plug in that A is 6. Also, so 6 right here, 6 right there. Sine pi divided by 7 times 6, negative that, times negative 1 equals velocity equals negative 2.60, negative 2.60 centimeters per second, centimeters, make sure that's right. Alright guys, now on to part C. Please ignore the little X, the red X over there. I made a silly mistake when calculating it. Yeah, sorry about that. But yeah, anyways, back to it. So, we have our equation for acceleration is the derivative of velocity. It's going to be negative w squared a w. In this case, it's still 1, so negative 1a times cosine of pi over 7 cosine of pi divided by 7 times 6 is 5. So our acceleration is going to be negative 5.41 centimeters per second squared. This is my last attempt, unfortunately, because I messed up twice because I was being very dumb. So we'll just hope this works. And as I thought, yes, it works. So that's, guys, how you do the acceleration as well. Yeah, that's unfortunate. Alright, the amplitude is gonna be this thing right here, the part before the trig function, the trig part of the function, and so that's gonna be amplitude. Amplitude is this part right here, so then this part is gonna be 6. So our amplitude here is gonna be 6. I'm confident about that. 0.00 doesn't really matter, just 3 significant figures, whatever you want to do. And then the period is going to be w, so w equals 2 pi over t, period. Therefore, period equals 2 pi over w. In this case, our w, since it's wt plus pi over 7, and this is just t, we can assume that w equals 1, so w 2 pi over w is 2 pi. So our period is going to be 2 pi, which is going to be 6.28 seconds. That's 6.28 seconds. And there you have it, guys. It's problem number 17. Now on to problem number 18. Vamos. The position of a particle is given by the expression x equals 2 cosine. Alright, so x equals 2 meters cosine of 4 pi t plus 2 over 5 pi. I really hope that's not 2 pi. It's definitely 2 pi over 5. Alright. Sorry. 2 pi over 5. If not, guys, I'll just redo the calculation. Whatever. No big deal. One mistake is not going to kill me. Actually, meters and T's and seconds. Alright, perfect. Determine the frequency of the period and period of the function. So, frequency is going to be, so we know that this is going to be our w value. W equals 2 pi f. Therefore, f equals w over 2 pi, which equals, in this case, 4 pi over 2 pi, which equals to 2. Because, yeah, cancel out a lot, 2. That'll be the frequency. Frequency of this function. Frequency is 2 hertz. We know that the period is 1 over frequency, which is 1 over 2, which I'll just do 0.5 here. That should be the answer to part A for that one. Now part B, amplitude of the motion is going to be 2 meters because it's just this value right here, 2 meters. Part C, turn the phase constant. Phase constant is 2 pi over 5, which is just 2 pi divided by 5, 1.26 radians. And then determine the position of the particle at t equals blah blah blah. A, B, C, D. You just plug in the value for time, so that's equal to 2 cosine of 4 pi times 0.35 seconds plus 2 pi over 5. X equals, do that out, we get 4 pi times 0.35 to power 5, so plus 2 power 5 cosine of this times 2 equals 1.62. So that's going to be 1.62 meters. Now there guys should be the answer to all our problems. And awesome, yeah. So now quickly guys, we're zooming past these 19. Problem number 19. Alright, so a 0.5 kilogram object, 0.5 kgs. Object attached to a spring with a force constant of K equals 8 Newton meters of force. Vibrates in simple harmonic motion with amplitude of 11 0.115 meters. At the origin at t equals 0. Alright, so that would be a sine function basically. So calculate the maximum value of its speed and acceleration. Alright, so A V max equals W A equals square root of K over M times A, which equals, oh, it's in centimeters, so we can leave this in centimeters, 11.5 centimeters. Will it matter if my, that's annoying. Because it's in the centimeters. Oh, whatever. I don't actually know. So we'll do that. 0.5 divided. Wait, no. 8 divided by 0.5. 16, 4, 11.5, 44, 46 centimeters per second, I believe. My math might be wrong, but yeah, no, 46 centimeters per second. There you go. You just plug in your values for K, values for M, values for A, centimeters. Alright. And then second part is for A max equals negative W squared times A, which I don't think, yeah. Oh, it's just going to be the absolute value of that, sorry. So A squared, it's like that, which equals, so W squared is 8 over 0.5, 16. 16 times 11.5, 16 times 11.5, 16 times 11.5, 184. 184 centimeters per second squared. Now guys, just using our equations again. The massive acceleration is that, well, 184. Yeah. Please work, yes. Alright, now B. We have part 1 of B. So in this case, calculate the speed and acceleration of the object is 6.5 centimeters from the equilibrium position. Ooh, copy that. Alright, so this means that we have to find the time, and then we find everything else based on the time. So we have a function here. Just waiting. At the origin at t equals, so yeah, it's gonna be a sine function, right? So 6.5 centimeters equals amplitude sine wt at the origin, so no phase constant. Do 11.5 here. 1.5 sine wt. W is 4 times time. Solve for time here. 6.5 divided by 11.5 sine 1 divided by 4 t equals 0.15. Now we can do our equations. V equals 11 point equals 46 because you take out the w. 46 cosine of 4 times 0.15. 4 times 0.15 cosine of that times 46. Velocity equals 38.0 rounded. 38 point. Oh, let me just make sure this works first before I do anything too dumb. Alright, does work. Okay, cool. Does that make sense, guys? I just took the derivative of our equation here. Since it starts at the equilibrium, I started at a sine function instead of a cosine function. That way I didn't have to do a phase constant. Derivative, so take out the 4, that's w, times the amplitude is 46, times cosine of that. Solve for v, because we're getting everything else. Take 38 centimeters per second squared, centimeters per second. Second part of v is going to be for the acceleration. Sorry, not that. The acceleration, which equals negative w squared a sine of w time, which equals 4 squared, so negative 16. Negative 16 times a, negative 184. 4 sine of 4 times 0.15, which equals sine of 0.6 times negative 184, which equals negative 103 negative 104 in this case because of the significant figures. Negative 104 centimeters per second squared, I believe. Yes. Alright, now let's do part C. Sorry, guys. New page, I guess. Part C, right here. Alright, so calculate time interval required for the objects to move from x equals 0 to x equals 4.5 centimeters. I believe that would just be the same equation, but then solve for t again. But so x 4.5 centimeters equals 11.5 sine of 4 times t. 4.5 divided by 11.5. 4.5 divided by 11.5. Arc sine of that divided by 4, 1.01. Wait, no. 0.101 seconds. I think, right? And that should work. There you go. All right. Yep. Perfect. Awesome. So now we can move on to question number 20. So, question number 20. Consider a graphical representation of simple harmonic motion as described mathematically in equation 15.6 below. When the object is at A on the graph, which of the following best describes position and velocity? Position and velocity are both negative. No. Position is negative and its velocity is 0. I believe so, yes. Position, actually, no. Oh, point A on the graph, my bad, sorry. Position negative, no. Position is negative, yes. Velocity is 0, no. Position is positive, no. Position is negative, velocity is positive, yes, that's true. Position is positive, velocity is negative, no. Position and velocity are both positive, no. For position, you look at where it is relative to the y-axis. So if it's if here we have, if A is anywhere in this region, x is positive, and in this region, x is negative. However, since the velocity is the rate of change of that, if it's going in this direction, v is positive. If it's going in this direction, downwards, v is negative. And if we're at the bottom of a curve here, v equals 0. That is how that works right there. So because it's just a slope essentially of the rate of change of both. So in this case, at that point down here, since it's in the negative region, the position has to be negative, but the velocity is positive, since the slope of this curve right here is positive, like that. All right, now on to problem number 21. So I already did this one, but consider graphical representation in simple harmonic motion as described mathematically in equation 15.6. When the object is at position A on the graph, its velocity is, like I said, positive, and the acceleration is, acceleration would also be, in this case, positive, yeah. Because it's still on a curve, it's actually gaining speed like this. That makes sense. But if you think about it, like derivative wise, here we have our cosine function. If we had a derivative of that for velocity, is sine function is negative sine function. So at this point A, the velocity would be positive, and then our negative cosine function of our acceleration is also still positive right here. Like, that's, if that makes sense. If you think about it, like, just visualize the graphs in your head, guys. If you if you're ever unsure how to solve these problems. All right, object of mass m is hung from a spring and set into oscillation. Period of oscillation is measured and recorded as t. As t, the object of mass m is removed and replaced with an object of mass 2m. When an object is set into oscillation, was the period of the motion? So we know that for 22, we know that t equals 2 pi square root of m over k. So if 2 square root of 2m over k, that means that we could that means that this equals 2 pi over square root of m over k times square root of 2, which is square root of 2 times this value of t, so therefore it would be square root of 2t in that condition, if the mass is doubled. Next up, figure 15.6. shows the position of an object. In this case, 23, I think that it'd have to be 0.5 and pi. I'm not entirely sure how to explain it. I assume like obviously it has to be 0.5 just because of the radius, but then pi. Alright guys, now on to question number 24. So what happens to the period of a simple pendulum if the pendulum's length is increased by a factor of 10? I believed if it's increased by a factor of 10, it'll be square root. Square root of 10 times that, yeah. Square root of 10 times, so 3.16 times t initial. 0.16 to length times 0.5. Then it has a period if the mass of the bob suspended is increased by a factor of 10. Nothing, I don't think. Yeah, literally nothing, so it just stays the same. Because mass does not affect the period. Yep. Therefore, alright guys, these four right here, 25, 27, 25, 26, 27, 28, are all basically all multiple choice, and they're fairly simple, so I think you guys can do those on your own. I'll move on to the other problems, go to the next page if it's available. Alright guys, now on to question number 29. So 29. Two spheres having masses m and 2m and radii r and r3 respectively are released from rest when the distance between their centers is 12r. How fast will each sphere be moving when they collide? Assume that two spheres only interact with each other. Okay, so two spheres start at rest. We'll have sphere 1 here. We'll have sphere 2 here. Center the masses. This is value r. R equals 12 radii. This is 3 radii. Since here is 1 radii. This one is mass of m, so the mass of 2m. Then they come together, they collide. We're left with one planet here, one thing here. Not to scale, obviously, because the distance is 4r between the centers of masses. That makes sense, right? Yes. Right here. So at the start, we can take the gravitational potential energy because they're not moving; they're at rest. So we'll take gravitational potential energy m and then 2m over 12r equals u sub g initial. So move that down here because it's going to be a big equation, I assume. G m 2 m over 12r. We can condense this to gm squared over 6r, we'll do that later, equals, so it's going to be gravitational potential energy initial equals gravitational potential energy final plus kinetic energy 1 plus kinetic energy 2 in the end, right? Right, I believe so. All right, now, yeah. Okay, so, anywho, oh sorry, I don't know why it was like that. So gravitational potential energy final is going to be same formula minus g m2 m over, in this case, 4 r because that's the end, plus, will one of them be negative because of velocity? I think so. I think one in kinetic energies will have to be negative, but we'll see that later, I suppose. Alright, so kinetic energy 1/2 mv final squared mv1 final squared plus 1 half 2 mv2 final squared. Alright, first thing I'm going to do is I'm just going to take out these 1 half times 2. Take out this will become 2 r, this will become 1, this will become 1, this will become 6. And then we'll subtract, we'll add this to both sides to get negative g m squared over 6r plus this is going to be 3 plus 3, well, plus because it's a negative here, plus 3 g m squared over 6r, I believe. Yes, which will equal to 2gm squared over 6r, we'll do it later, equals 1 half mv1 final squared plus 1 half mv2 final squared. So, I'm convinced that one of these should be negative, but I'm not entirely sure. So if it be negative velocity, yeah, so one of these will be negative, but then velocity is squares will 1 matter. Never mind, sorry about that. Yeah, because kinetic energy is, yeah, never mind. Okay, so now we have 2 unknowns, the velocity 1, velocity 2, and that's what we're literally trying to find. So in order to find those, we can use the law of conservation of momentum. So we have, we know that m1 velocity final 1 plus 2, well, m1 is m plus 2m velocity final 2 equals 0, because that was the initial momentum, and then now this is the final. At the collision, wait, it's initial, well, initial final collision, I don't really know. Yeah, fine, initial final during collision, because I'm just like, all right. So sorry if I did a terrible job explaining that, but yeah, law of conservation of momentum now. We can get an equation for v2, we'll do that, or v1, whichever one you prefer, honestly. Start off with v final 1 equals negative 2v final 2, it looks like, because the m's will cancel out. Yeah, alright, and then we can plug that back into our equation up here to get, here, do this, g m squared will be 2 over 6, so 3r gm squared over 3r, like that, equals 1 half mv squared. This is going to be v. It's 4, 2 with 2 m v f 2 plus 1 half mv squared f mv 2f squared, just like that. So wait, no, I need to remove the 1 half. What am I doing? 3 divided by 3 is 3 of those divided by 3. It's gonna be 9 of those. 9, cancel out 1 m for each. 3, 9, square root of, so that should be velocity squared, velocity of 2 equals square root of g m over 9r, I believe. Well, let's check that. Square root of gm divided by 9r. Yes, alright, perfect. And now if we want to solve for velocity final 1, and also guys, after this point, it's basically just algebra. Just plug this back in and bam, just calculate that out. It's really just all algebra from there on. So we have velocity final 2. Oops, sorry, velocity final 2. We know that we can probably just plug it into here, I assume, right? Yeah, that'll probably be the easiest. So velocity final 2 is that. M1 VF1 plus 2M negative 2. Alright, and then velocity final 2 square root of GM over 9R equals 0. So velocity final 1 equals negative 2 square root of GM over 9R. But it asks how fast they're moving, so although this is negative, but this will become positive since we're going to take the magnitude just to find the speed. So velocity final is equal to GM over 9R. Voila. Now this could be simplified, guys, to 2 over 3 square root GM over R, but it really does not matter, guys. Really does not matter. And that, guys, should be the answer to question number. I'm blanking right now. It's getting a little late. Question number 29. Sorry. All right, and there you have it, guys. Velocity final 1, velocity final 2. Here's the last little glance at it. Before we move on to now question number 30. All right, let's get it. So 30. A ring of matter is a familiar structure in a planetary and stellar astronomy. Examples include Saturn's rings and ring nebula. To consider a uniform ring of mass 2.24 times 10 to the 20 kilograms. All right, so 2.24 times 10 to 20 kilograms. Where distance, where point A, point B out here. You guys might remember this question from the gravity and satellites Webassign. This is the exact same question basically. So we're just gonna do it again as review. It's part of this Webassign as well. So let's do it. All right, so we have an object. Its mass 1,000 kilograms. This thing has mass 2.24 times 10 to the 20th kilograms. Radius 10 to the 8th. To the 8th meters. And this distance right here is 2 times 10 to the 8. Alright, so we're going to find this distance for R right here, because it's going to be distance from any point. So it's going to be 10 to the 8th squared plus 2 times 10 to the 8th squared, all square rooted, equals R, which equals, in our case, 10 to the 8th, 10 to the 8th squared, 2, and that's going to be 2 times 10 to the 8th squared, 5 times 10 to the 16th equals square root of 5 times 10 to the 16th, 5 10 to the 16th, square root of that is going to be 2, 2, 3, 6, 0, 6, 7, 9, 7.7 meters. All right. Let's see what they're asking now. Calculate the gravitational potential energy of the object ring system when object is at A. That's going to be the R, so it's going to be gravitational potential energy. It's going to be A G M 1 I won't use a big M in this case, I'll use M2. M2 over R. Our R value is this. Oh, it's negative, sorry. Equals negative G times 1,000 times 2.24 times 10 to the 20th kilograms all over 223,606,797.7, which equals 1,000 times 2.24 times 10 to the 20th times G divided by this value times -1 in joules. 66860 66860 joules, which you can round or not. And that, I guess, is correct. That's going to be the answer to part A. Now for part B, let's do this. Gravitational potential energy with systems at a distance B. So in this case, it's here. It's going to be, this is going to be a value R right here, which is going to be the radius, which is 10 to the 8th. Same process. Gravitational potential energy of B equals negative G M1 M2 over 10 to the 8th now, because that's R, which is, we'll use the same values up here, so I won't write them out this time. G times this times this, so I have it up here still. This calculation, we'll write that down. Divided by this time 10 to the 8th. 10 to the 8th. Just gonna be times -1 negative 14,90504. That's the answer, guys. Negative 14,90504. Significant figures, I try to stay within like 3 or 4 sometimes, like here negative 14,995 maybe, just for aesthetic pleasure, like that. Bam. And now for part C, calculate the speed of the object as it passes through B. So we'll use we'll do the gravitational potential energy at the start is equal to the total energy at the end. So UG at A equals UG at B plus K at B of the little thing. So negative 66860, because we already have the values of UGA, UGB, put that in, and then negative 14,950 plus 1/2 small m 1000 v squared final. Solve for v squared final, so we add this to that, so we get this minus negative that, add them, bam, times 2, and then divide by 1000, square rooted, we get velocity final equals 12.8, well 12.9, velocity final. I'll write it all out actually, 12.85643,461, which is equal to about 12.9 meters per second. Voila. 12.9 meters per second. And that should be the answer right there. And voila, guys, that is the answer to problem number 30. Now, guys, alright, guys, now on to problem number 31. So, imagine that a hole is drilled through the center of the Earth to the other side. An object of mass m at a distance r from the center of the Earth is pulled toward the center of the Earth only by a mass within the sphere of radius r, the reddish region. Write Newton's law of gravitation for an object at a distance r from the center of the Earth and show that the force on it on Hooke's law form F equals negative kr, where the effective force constant is blah blah blah. Here is P, the density of the Earth, assume for uniform, and G, gravitational constant. So with that, we have Newton's law of gravity. Force gravity is G m over r squared. In which case, m is the mass of the Earth, and the mass of the Earth is the volume times density, which in this case equals volume of a sphere is 4 pi r cubed, 4 thirds pi r cubed, right? Where this is the radius of the Earth, I believe. Well, how do I say this? Yeah, 4 pi r cubed radius times the density, because that's the volume times density, which is in this case P, right? Yeah. Constant P. Therefore, I can rewrite this equation as G 4 thirds G pi r cubed P over r squared. Cancel out the exponent with the bottom, which therefore equals 4 thirds G pi P and m, sorry, I forgot the m as well, times r. In this case, this equals k times r. Voila. This proves that this part right here is in fact k. Now, the part B of this question, well, the second part of this, show that a sack of mail dropped into the hole will execute simple harmonic motion if it moves without friction. That I do not know how to show. I will be asking my professor, my teacher, sorry. I'll ask my teacher about that, but I don't know how to show that, and I don't know how to do it on paper. For part B, I think I can solve it. Show that a sack of mail, when will it arrive at the other side of the Earth? So, it's 2 pi I'm sorry. Over G 2 pi times what's it called? Radius over G, because the height you dropped it from. L G radii. Would it be 2 radii? No, the amplitude would be from the middle. Okay, so that's starting at the top. It's like a cosine function. Yeah, just like that. Okay, cool. So we're on the right track. Period. We're gonna take half the period, so we can cut this out. Half t. What's that? And now we just take pi times square root of r over g equals almost pulled the phone. It's not a calculator. So square root of the radius of the Earth divided by 9.806 times pi seconds divided by 60, 42 minutes. Yeah. 2.531 seconds equals 42.2 minutes. There you go. That is it, my friends. And no, it would not be 2. I don't know why I wrote that down. Well, I do know why, but I know why it's not. Alright, guys, and yeah, that concludes it. There's nothing else to really, yeah. Alright. Alright, guys, thank you so much for watching. I hope that helped in some way, shape, or form. I hope that you really enjoyed the video. And guys, please let me know down in the comments below if you liked the new format instead of me writing on the board. If you like me just like writing on paper with the problem up side by side, because I can do that still. I can try doing it on the board while up side by side as well. That could work. Just let me know whatever works best for you guys, whatever you guys prefer. And yeah, please leave a like and subscribe if you enjoyed. Share this with anyone who you think could use it, not maybe need it, but who could use it. Yeah. And then if you have any questions about anything, like in particular, like any topic you'd like me to cover rather than just going over problems, please guys, please feel free to let me know. You can reach out to me on any social media platform. If you have my number, text me. If you otherwise, you can just drop a comment down below and let me know any questions you guys might have, anything you guys want me to add. So yeah, thank you so much for watching, guys. I'll see you next one. Peace.